Swayam Prabha. Digital India. Educated India.
So, just to give you a brief introduction, I am Arvind Pattamata. I am a faculty member in the mechanical department here in IIT Madras, and this is Professor Marco Marengo. He is a visiting professor from University of Pavia in Italy, and he has been associated with us for the past 1 year, since January 2024. As you all know, Professor Marco is a leading expert in the area of multiphase flows, especially focused on sprays, droplets, and also on thermal management systems like heat pipes. So he is a renowned expert in that area, and we are very happy to host him here. And also he has agreed to offer this GYAN course on a very important topic, which is on multiphase heat transfer. Because we know when we are in graduate course, when we take graduate courses on heat transfer or fluid mechanics, multiphase flows is not usually covered in a classroom setting in text, in textbooks also, unless you are specifically taking courses or electives related to multiphase flows. And these are not very common in many universities across the country, except for a few IITs here and there. So the reason why we are offering this course is to probably bridge that gap, and increasingly we are seeing a lot of young researchers working in the area of multiphase flows. Like, I think most of you are mentioning you are working on dispersed flows or heat pipes and so on. So without the adequate bridging knowledge between what you learn in a graduate program and what you are working on, so sometimes your understanding is not complete, and you may still have a lot of fundamental doubts about your research problem. So one of the reasons these GYAN courses are being offered is to bridge this gap, because there is a big gap between the fundamental textbook knowledge and then the practical applied research that you do, and the kind of rigor that it requires for you to develop your knowledge is not usually offered in a general classroom setting. And that's the reason this GYAN courses have come up, and last 5 or 6 years it has been tremendous success. We have maybe a few thousand courses, and in fact I had offered one in 2023 with Professor Peter Stefan on micro nanoscale energy transport, and this time we wanted to offer something on multiphase heat transfer, because multiphase heat transfer is something now almost in mechanical department, applied mechanics, and even aerospace. So a lot of research is being now carried out, and it's high time that this bridge course can be used to make sure that we give you some insights into not only just the fundamentals of multiphase flows, but also on some applications on thermal management as well as heat pipes and so on and so forth. So in that respect, this is just a brief introduction that I gave you about ourselves. So this course is a 1-week course. It's designed to run on 5 days. So this is the first day, 13th, and then it will be running continuously until the 17th. And I'm sure that we have a lot of festival holidays in the next 2 or 3 days, but that also gives us some quiet time in the campus so to run this program. And I'm sure that most of you are already finding a place to accommodate yourself. We couldn't provide direct accommodation, but you are able to accommodate either in the hostel or somewhere outside in the nearby. Yeah. So all 4 from ISRO, right? Yeah, please come. So this is basically some kind of introduction that I wanted to give. The other important thing is there are some of you who are come here to credit this particular course for earning a credit and a grade for this. So are there anybody who is interested in that sense, that they have to write an exam on the last day? So once you write the exam, then we will evaluate and then give you a grade. So are there anybody who is interested to credit it? Because this is technically, according to our IIT standard, this is a 3 credit course. I mean, in the new credit system, or for the other universities it may be 1 credit, because typically how we calculate 1 credit is we run typically 3 hours of lecture in a week, if you calculate it that way, it's 1/3 of your total number of lecture hours in a semester, which is typically 13 to 14 hours. So this is a 13 to 14 hour lecture program, so which carries a weightage of 1 credit. So if you are having 3 credits, typically it's 39 to 42 maximum number of lecture hours. So if somebody is interested to use this as a 1 credit for their university system to earn a grade, are there anybody interested? Can you please raise the hand or no? So as of now only 2. So then in that case, if there are only a few people, then we will try to have a Viva OC or something and give a grade rather than a written exam, because typically the written exam will be more useful if there are at least 10 students who are interested. Then we can set a question paper and we can evaluate it. But if there are only a handful, we can just
we can do an
oral exam and then we will evaluate it. But that will be after the course is over, typically in the afternoon of 17th.
So Friday.
On Friday. Okay. So anyway, just to give a very brief outline about the course content. So I will just go through this course content, and after that, if there are any questions related to the operation of this course or course content, you can discuss, and then I will hand it over to Professor Marco to officially begin the lectures. So this is, as I said, a 5-day lecture program. So in the sense that we are not running on a 5-day from morning 9 to 5. So it is just 3 hours on each of these days, and we start today, the first day. So first day is primarily devoted to some introductory concepts related to setting the background for this course on multiphase heat transfer. So there will be an introduction to heat transfer primarily, followed by a very important understanding of thermodynamics. I think most of you have learnt it, but probably you need a refresher again. So some concepts related to thermodynamics are required for looking at how phases exist and phase transition and things like that, and then we get into the concept of phase change. Okay. So this will be covered extensively for about 3 hours, and tomorrow, the next day, we will be covering some concepts related to fluid dynamics of diabatic flows. So that means flows which involve heat transfer. And we will also have some concepts involving multiphase flows. The actual concepts of multiphase flows will start coming from the second day, and on the third day I will be covering concepts related to phase change heat transfer. So primarily boiling and condensation. We will start with pool boiling, which is the more simpler form of boiling concept that you can understand. Then we will get into flow boiling or convection boiling. We will talk about flow boiling in conventional size tubes and in small size tubes like mini channels or micro channels. Then we will talk about condensation. So this is on the day 3. We will talk about phase change heat transfer, and then on day 4 again Professor Marco will talk about concepts related to interfacial phenomena, introduction to fluid dynamics of diabatic flows with phase change, and CFD modeling of multiphase flows. So these are all some important concepts that are required as a practical researcher. So he will be touching upon these topics on the 4th day, that is on Thursday, and Friday is the last day of this course. So I will be covering some introduction to thermal management. So these are practical applications of multiphase heat transfer, followed by the measurement techniques on multiphase flows and heat transfer. I think some of you are actually also working on experimental methods, and you may be interested to know what kind of measurement techniques that we generally want to use when we deal with multiphase flows. So we will cover some of these in this particular lecture, and then Professor Marco, who is an expert in heat pipes, and most of you are working in heat pipes, will also give an overview about heat pipes and practical applications of heat pipes. And as I said, I think if anybody is interested in taking this course as a credit or transferring this credit to your university and they want to give an exam, given that only a handful are shown interest, we will have a oral exam on the afternoon of Friday. Okay. So this is going to be the basic outline of this course. I'm sure I've shared this outline also with all of you, and there is hopefully there is no surprise in this particular course structure that I'm showing now. Are there any questions from any of you? Anything that you would like to expect? Any expectations from you in this from this course or so on?
About me, I'm a distinguished professor of thermal physics at the University of Pavia. I'm working in this area since 30 years now, and mainly about sprays and heat pipes. So these are my main topics: sprays and droplet impact. Okay, so I started with my PhD in drop impact, then I went to microfluidics, and then microfluidics with heat transfer, both experimental and numerical. And then in 2008 I started with heat pipes, with pulsating heat pipe, and now I have two roles, let's say maybe to mention today. One is that I am the principal investigator for the pulsating experiment on the International Space Station, that I hope that will be on board in 2027, depending on the logistics of the space station. And also I am the international president of the ILAS, the International Organization for the Space System, Atomization and Space System. So these are the two main roles that are interesting for you here. So as said, we can start. Again, I will be very fast this morning, because I would like to catch up a little bit more, let's say, about the things that we are going to say in the next days. So why study multiphase flows? Let me sit down. But no, I think that because there is no pointer, so there is no stuff to. I'm like an actor. I like to move and so on. But now I need to look at the camera, otherwise we have a problem. But okay, bear with me. So multiphase flows. Multiphase flows are really everywhere. So you can think about bubble rise and boiling, condensation. Only saying boiling and condensation, evaporation, and you can see really how many possible applications you may have, from the refrigerators and so on. But also in nature, no? You have a volcano eruption, rain formation. Today there was a lot of nucleation. I spoke with Arvin because there was fog, but there was also smoke, and the smoke is acting as nucleation site for the humidity. And so we had, when I woke up at 6, when they went to the balcony there was a lot of smoky fog, and they said, "What is happening?" Then I was not thinking to the Pongal and so on. Someone is burning some stuff around. So energy, wow. Energy is full of multiphase flows. This field is with oil extraction, nuclear cooling, wind turbines, and so on. Space exploration, someone is from ISRO, so the thermal controls of a system, fuel management in spacecraft, and multiphase flows in this case are, for example, linked with the microgravity, which is a kind of very different environment for many physical processes. And then we have aerosol in sprays, HVAC system, and so on. So only to tell you, it's a very rough estimation, but when you are writing a project about multiphase flows, something to say is that is a trillion of trillions, not trillion, not one, many trillions of dollars of economy is around application with multiphase flows, okay? Oil and gas, aerospace, pharmaceutical and food processing. Imagine when you have your instant coffee, no? Let's say the process to have dry coffee and so on. Or for example, a lot of pharmaceutical. For example, when you have the powder, to produce powder, this is a multi-phase flow system. When this is the multi-phase flow process. And then pollution, carbon capture, water purification, and so on and so on. So again, 30 hours, no, 13. So what I'm saying, 15. to describe something like let's say the entire field of multiphase flows, of course, is very optimistic. No, for example, I contributed to this encyclopedia of two-phase heat transfer. I did some 2 paragraphs about a Passetini pipe, and so in my course I have 60 hours to speak about that instead of 15. So only to give you an idea, that will be quite difficult, and this is plus minus my situation. And because it will be very tough to cover everything. So this is the reason, because I will stay later after 12 in order that then you have time, maybe with if you are doing say a PhD on this, if I can, let's say, help you in this, I'm very happy to do it. So we are speaking about multiphase flows, and in fact multiphase flows are really a big variety of possible flows. This means multiphase means that we have different phases, okay, and different components, okay. So, for example, if you are thinking to gas-solid flows, we have fluidized beds, where we have particles, solid particles, and we have air, gas, something that is going to push these particles around, okay. This is very classical, for example, in the production of powder, or maybe we can even have a spray. So we have a liquid spray, gas, and solid particles. Or if you are thinking to pneumatic transport, we are conveying particles like grains or powders using air again. This is again is a possible application. So multiphase flows means not only liquid and vapor, no? But means really a plethora of a possible application, like gas-solid flows. Then we have liquid-solid flows, slurries, for example. Here we can see, for example, cement pumping. Sedimentation, particles that are settling down in a liquid, in a pipe. For example, we would like to transport particles, for example, for cleaning processes. We have even, I work in radiator leak mitigation, where we are using very small particles and fluff and so on in order to go to the points where you have the hole and to obstruct, to close the holes. So in order that you don't have any leak. So there, for example, you are using liquid with solid particles in order to bring them in the position where you have a hole somewhere. You don't know even where exactly, but it's happening that these particles are going to close the system. So then we have liquid-liquid flows. So we have emulsion. Imagine all the chapter about oil-water mixtures, where we have dispersed droplets and immiscible fluid. We have stratified flows, or we have something before the mixing and so on. Again, this is a multiphase flow. So you can imagine that in 15 hours we cannot speak about emulsions. There will be no time, for example, for that, even if it's really very important. So microfluidics. We saw application at the big scales, no? A big reactor producing coffee or producing a drug in the pharmaceutical companies, or some powder for the food, okay? But also we have something very small. So the problem of multiphase flows are really multi-scale. They are going for meters up to, let's say, micrometers. So this is another point where, let's say, we can understand the multiphase flows are really very complex. This is, for example, a work that I'm doing just now. It's about the production of micro droplets. Let me see if it's starting or not. Yes. No, I need to use the mouse here. Okay. So, start, yeah. It's a bit slow, I don't know. Here what we have is that we are using, let's say, the system where we have mineral oil plus a surfactant, so we have a liquid, and then on the other side we have nanoparticles of CaCO3 that are building up with the acetic acid. They are going to be focused in this point, and they are producing droplets. Why? This system is for example DNA, RNA trap. So, for example, we would like to get the RNA, for example, when there were COVID, remember that they have this RNA that was used as a vaccine, okay? You would like to trap this RNA inside the droplet, okay? How to do that? The point is that you need also to protect, because RNA is very weak. So someone used cryogenics, I think Moderna used cryogenics to protect the RNA. But for example, another way is to put inside hydrogel, is another way. So you need to protect. So the CaCO3 is with alginate is important because it's going to trap the RNA, and then we are going to put, for example, with UV light, we are going to have a crust of CaCO3 in order to protect. So at the end we have a kind of droplet with a shell. What is more than this is really multiphase flow. This is a real multiphase flow with particles, with different liquids and so on. Then we have gas-liquid flows. So in this case we have bubbly flows, we have air bubbles in the water, in a liquid, slug flow, we have large gas pockets, we have annular flow when we have a gas core surrounded by a liquid film, and then we have sprays, atomized liquid droplets in air. And here is only to say that, for example, what is happening at nanoscale is very important. This is a fluctuating hydrodynamic simulation of boiling, and this is a system where we are going to use, this is not working, I checked before. No, it's blocked. Just a moment. Now. Okay, we can't play. Okay, sorry for that. I know that when you transport the presentation from the computer to another, it's always a problem. I checked everything, not this one. Okay, it's the only one that is not working. But okay, here what we are doing stochastic hydrodynamics. We wrote the Navier-Stokes equation with diffuse interface and fluctuations, so we are able to simulate the boiling at the nanoscale. Because, for example, as you will learn from Arvind, what is important in boiling is what is happening at a very, very small scales. And sometimes the scale are, let's say, something very difficult to measure because it's not anymore microns. We are speaking about nanometers. Imagine to have, let's say, a nano bubble, and you need to explore what is happening there. It's very difficult. And also, maybe the boiling is starting from the very few air bubbles, the gas bubbles that are inside the system as dissolved gas, because it's very difficult to put away all the gas that is inside. So this is again a very sophisticated, for example, way to see the multiphase flows at the nanoscale even, not anymore at, let's say, a microscale. And then what about all the fuel, the injection, and so on? No, I started, in fact, my PhD, I started to study droplet impact because there was a first engine, high pressurized gasoline, and it was in 1994, where we have Mitsubishi with this crazy idea to have 80 bar for the gasoline injection. And okay, the problem was that at the time, the injection was so fast that the droplets reached the piston ball, and so produce more emission than less emission, because they produce a liquid film on the piston surface, and this was very detrimental for the emission. So I started to study the droplet impact because of that. So then I entered in the field of sprays and so on. So imagine about sprays. For example, we have the pesticide sprays, the crop protection, asthma aerosol, deodorant sprays, high-speed dentist sprays, and so on. Again, multiphase flows that are very, very interesting for many applications. These are, for example, the first two on the top. They are very important for environment and so on, to avoid, for example, overspray, which is the right dimension of the droplet when they are, let's say, going to the crops, no? And they are not going everywhere with the pesticide. Of course, this can be a big problem. Then we have gas, liquid, solid flow. So when we have everything together, you saw already before, we have a liquid spray with gas and particles. In this case, for example, we can think to foams, Or, for example, there are applications like cavitation, aerosols, that are also, let's say, multiphase systems. So there are really so many possible applications, okay? And there are a lot of studies. I am the associate editor of the International Journal Multiphase Flows. So I'm receiving, let's say, 10 papers per week about this topic, but it's only one part of the let's say, I think that is more than 1,000 papers are dealing with multiphase flows per year that we are receiving, okay? And I'm also associate editor of MDPI Energies, okay? So, and there, again, we are receiving, let's say, I don't know, 100 papers per week about multiphase flows. Imagine the quantity of data, information, and so on. 60% are rejected. Okay, but let's say, in any case, we have at least 40% that are going through. And so there's a lot of data information. So the topic is really huge. It's really huge. And in fact, also, from this audience, it's very clear that someone is working in heat pipes, someone else in sprays, someone else in the other topics, maybe numerical, experimental. So it's very difficult to cover everything. So let's do the first very short introduction. The first 3 lessons were intended to be bridging lessons again, but in front of this audience, I think that I'm going to be very fast. But I need something because I need something also for the lessons of tomorrow. So I think that you know everything here. So, as you know, heat transfer, what is heat transfer? Is a thermal energy in transit from one system to another because we have a temperature difference, okay? Thermal energy is associated at the molecular level, at the atomic level, what is happening in terms of kinetic energy. Something that, of course, you know, so I will be very fast here. So I'm using the symbol U for internal energy, of course, temperature T, the heat transfer, we are going to have the heat Q, the units are the joule, and the heat rate is the Q small, and the heat flux is, of course, Q. I'm using this notation. If it's not clear, let me know, but it's about the Q with the 2 apex here, so it's a watt over square meter. So, as you know, that we have 3 modes for heat transfer. One is conduction, convection, and radiation. I'm not going to speak about radiation this time. Sorry for that. If you have any problem, we can speak about that, but there is no time. Okay? So I'm going to focus a little bit more about conduction today and more about convection, because it's very important also for them for boiling and flow boiling, condensation, and so on. So, about the conduction, the heat transfer can happen in solid or in a liquid, in a stationary fluid. It's always difficult to have a stationary fluid, but this means that in a stationary fluid we have both conduction and convection, okay? So, but we need to think about that sometimes. In a solid is very clear, and we have this link between the heat transfer and the random motion, stochastic motion of the atoms inside the solid. Convection. In the convection is a form of conduction, only that we have also the movement of the bulk of the gas and the liquid. And so we have both the, let's say, the transport of matter and the transport of kinetic energy at the molecular level. And then we have the radiation, where we don't need any matter, but we have the transfer of energy to do photons, so electromagnetic waves. So Fourier equation, I think, okay, we said that in terms of, let's say, very generic, but of transport of energy because of the molecules and so on. We can think about the rate of conduction, which is in fact linked to the geometry of the medium, the thickness, for example, the material, the temperature difference. And we have the first law. The first law, or also called Fourier postulate, sometimes we are calling for postulate because he didn't know about molecules and so on. So the idea for him was, oh, I can say that the power that is transferred from one system to another when we have a difference of temperature is equal to the something, a parameter, or say proportional parameter, multiplied by the area of heat transfer, multiplied by what? Well, was not obvious because, for example, Newton would say something similar, but he said this must be proportional to the difference of temperature, which is still what we are using for convection. Okay? So everything that we don't know, we put in the H, in the heat transfer coefficient, so the convection heat transfer coefficient, and the convection heat transfer coefficient contains everything. All our ignorance about the problem is there. Okay? And Fourier said, no, it's depending also on the thickness of the wall or the thickness of the system. So it must be linked to the gradient. Now we know that this equation is valid because the system is in equilibrium. This equation is not valid anymore if the system is completely out of equilibrium. So there are, let's say, we need to say that because in multiphase flows, nothing is in an equilibrium. So we are trying to stretch the equilibrium, thermodynamics, to the multiphase flows, even if we know already that is not the case. So we need to pay attention. Many times it's possible to use equilibrium thermodynamics. We will see next hour. Okay. Sometimes it's delicate. One should pay attention. So, and this is a very important law. Because from this law, I will be very fast. From this law, we can have the conservation of energy transport, linked, for example, to conduction in a medium. Okay, so the Fourier equation is based on the assumption of continuum. Okay, so pay attention that is also linked to the fact that we have instantaneous heat propagation. Okay, and so it depends also on the relaxation time of the system. Or if, for example, if the system has a very low pressure, the free mean path of the molecules is very long. So this equation is not valid anymore. So you should pay attention. For example, when you have a vacuum system and so on, the few molecules that are going around, they are transmitting also heat, but in a way that is not described by the Fourier equation. Okay, so and also there are, let's say, other matter like, for example, semiconductor and so on, where we don't have only one kind of transport of energy. It's not, let's say, the energy linked to the kinetic energy, but also something related, for example, to vibration. So we are calling phonons. Okay, so the conduction is also linked to the vibration of the crystals inside the system. Again, I think that everybody knows that, but it's to bridge your knowledge now, okay? So if you have any question, please ask me, okay? And another point is that at nanoscale, the thermal conductivity is a function of material thickness. So the K that you saw before, this K, is not constant anymore at nanoscale, but depends on the scale. It's not one value anymore. It depends on the scale, it depends on the frequency, it depends on the rapidity, so it depends on the flux. So it's becoming really a very complex problem because you're thinking a flux is proportional to the area multiplied by the gradient, and the proportionality is K. But then K is depending on flux, and it's depending on the scales. So it's depending on the X. So at the nanoscale, this equation is becoming difficult now to interpret for all the possible cases. Well, but let's say that for what we are going to see in the next days, the Fourier law applies, and then we have that we can use this very nice equation. The flux is proportional to the heat flux is proportional to the gradient of temperature, and everybody knows here that the minus is linked to what? To the second principle of thermodynamics. Okay, so the heat is going from the system at high temperature to the system to low temperature. There is no other way. Okay, So it's the second principle of thermodynamics that is deciding the direction of the heat. So you can write this with the different coordinates. I will keep this, let's say, in PDF. We are giving a PDF to you. And I think that is interesting because then you have a kind of lesson, introduction, complete introduction about heat transfer, thermodynamics, phase change, Navier-Stokes equation, and let's say, I think that so there are many more slides in my presentation than what really we are able to pass and to describe, but I think that is important for you because maybe this afternoon you can read again if you have some doubts, or tomorrow you can ask me questions. So the heat equation. It's possible to derive the heat equation, let's say looking at the balance of the fluxes on a small volume, or a small area, in this case is a 2D. Okay? What is the heat equation? The heat equation is the equation that is describing how is evolving in time and space the temperature in a given system. Okay? So I don't have time to pass, let's say, the demonstration, but what is important to say that we can use what we know in terms of balances, and we are landing with an equation that in fact contains the second derivatives of the temperature in the three directions. Again, this is something that you should know, and I will pass very fast. So at the end we are going to have this equation, and you can see here that the K, the thermal conductivity, is inside the derivatives here. And this is very important to say because when K is constant, is not a problem. So the K can go out of the derivatives. But if K depends on the direction, then it's becoming very important. So for example, for an anisotropic system, the K is something that you need to check because there's a Kx, Ky, and Kz. Okay? This is a very good way, for example, to understand if a diamond is a fake diamond or is a true diamond, you know, because it's the perfect way to test it is to use a sensor that is measuring the conductivity, because if the diamond is not a fake, there will be a strong difference in two planes for K. So it's very anisotropic system. So K in one direction is much bigger than in the other direction. So if you test one direction or the other, you're going to test to have different K, different values of the thermal conductivity. If it's amorphous, because it's very nice but it's glass, for example, or something else, then you can understand that it's not a true diamond. And also at the nanoscale, again, K is not possible to put out the K from this equation because K depends on the directions and the motions and so on. So you need to have the K inside. When we have a one-dimensional conduction, as you know, the equation is very simple. We have a linear behavior. Of course, we are now thinking in stationary condition. So I think that this is really for, let's say, a very basic classes of heat transfer for the bachelor degree. So I don't want to spend time on that. What is also important are the boundary conditions, of course, the initial conditions. You know that we have Dirichlet, Neumann, Robin conditions, no? And we need to apply this condition in order to solve the heat equation for the different cases. So, in the heat equation, we have the Cp, rho Cp, that is linked to the term of the equation that is about the variation of the temperature in time. Okay? So in fact, this is linked to the thermal inertia. Okay? Rho Cp is linked to the thermal inertia of the system. So this heat capacity is quite important. We are going to see in the next hour how we can derive the heat capacity, but we can say now that heat capacity is the ratio between the heat that is transferred to the system with this variation of temperature. So this was, let's say, a thought of Joule from the very beginning when he tried to convert work and heat, okay, and vice versa. So We have heat capacity at constant volume and at constant pressure. Pay attention that we have when we have the phase transition, as you know, Cp is not defined or is very, very high, or in the ideal case, infinite. So we cannot use Cp anymore. Okay? For a closed system, we can write that Cv is nothing else than the molar specific internal energy, U, the partial derivative of U with respect to the temperature. There are a lot of possibilities to calculate the heat capacity, especially for simple materials, okay? And there were many tries, and people tried to explore the way to measure, to have an idea of this heat capacity. And already in 1819, so before Joule, Dulong and Petit found that for many solids it could be something like 3R, so a value that was almost constant, very interesting because it was also related to the gas. So for them was something unusual. And then Einstein did a calculation about Cv and was very clear, for example, that Cv was going to 0 when the temperature was approaching the 0 Kelvin. And in fact, Einstein formula is not really the best, but it's quite accurate already. But is not, let's say, there is a deviation, can be also an important deviation, about 20%. But because it didn't include, for example, phonons. So for, let's say, solid materials can be a problem to use the Einstein equation. So we have the Debye correction. And it's possible to have an estimation of the difference between the two heat capacity, one of the constant pressure and the other one at the constant volume, because they are linked using, let's say, thermodynamic relations. And here you can find values of the thermal capacity for different kind of systems. Again, during a phase transition, the heat capacity shows a peak. Of course, ideally is tend to infinite. Thermal diffusivity, in the heat equation, you can find alpha. Alpha is the thermal diffusivity, and is K divided by rho Cp. So the conductivity, thermal conductivity divided by the rho Cp, this term linked to the thermal inertia. Okay. The thermal diffusivity is linked to how fast is the propagation of heat inside a medium. Okay, so we can use the diffusivity to understand how a system is evolving in time in terms of temperature. Again, very fast here. You're going to see this later on, and so on. We are going to see that. In this field, we are using as much as possible dimensionless numbers. Okay, here you can see Fourier number, so the diffusivity multiplied by time divided by the length of the characteristic length of the system squared. But we are using BO number, where you have the heat transfer coefficient for convection multiplied by the characteristic length divided by the solid thermal conductivity. So we are going to use many of these numbers also in the next lessons. And these are values that you can find about the thermal diffusivity. What is interesting about thermal diffusivity that we can have an idea of the evolution in time when we are changing the condition with the solid. For example, this is a classical case of semi-infinite solid. In this case, for example, at the given initial time, you have a temperature that is different with respect to the rest of the system, and so we are having kind of wave inside the solid, a thermal wave inside the solid with given characteristics. Again, there is no time now to enter in this field. Thermal expansion coefficient is also very important. We have in fact two kind of thermal expansion. One is the volumetric, the other one is linear thermal expansion coefficient. And for isotropic material, the volumetric thermal coefficient is 3 times the linear thermal expansion coefficient. Thermal expansion, sorry, I forgot an N there. When we are dealing with phase change, usually we are dealing with a change, for example, from one phase to another. How many phases has water? 11, 12, I think. Something like 12 phases. Yes, about 12. I think that they are discovering new phases every time. So every 10 years there is someone, I discovered a new phase of water. Oh, okay, thank you. There are, let's say, different phases because, let's say, we have different kind of crystals. So, I mean, when you are changing a solid from one crystal to another, you are going to have a phase change. It's again a kind of phase change. This is happening also with polymers, for example, no? When you are melting a polymer, before going to the liquid, you have at least one other phase change in between, okay? So, phase change, let's say, the usual way to see is that we have four phases. We have solid, liquid, vapor, and plasma, okay? These are the 4 classical way. But then in the solid, we have different phases if you consider different forms of crystallines. So different forms, the different configuration inside the solid. So this is the reason why the water has now, I mean, I think 11, 12, maybe even more. If you look at Wikipedia, maybe now, I'm not sure, but it can be even more than 12. Okay. Of course, with very, very high pressure and very high temperature. So you need to go up, up, up. But it's interesting to know. What is happening with all the system is that when we have, let's say, something that is going from the liquid to solid, the density of the solid is usually bigger than the density of the liquid. But this is not happening for water. And this is the reason why when we are observing the universe and we are looking for exoplanets that may have some kind of life, we are looking for water. Why? Because the fact that the density of the solid water, ice, is less than the density of the liquid was the fact that allowed the life in this planet, on this planet. If there was the opposite, you can start having the ice, and then the ice is going down in lake, in the sea, and so on. And in 10,000 years of the icing time, you're going to cover up all the ocean and see you. But there is no form of life, or maybe only bacteria, but of course not other forms that are more evolved. Okay, so this is interesting, and this is happening because usually we need to consider the rearrangement of the molecules, of the form of the molecules when we are passing from liquid to solid. I put some slides at the end. I have 2 minutes, so I don't have time to explore this, but if you are interested, of course, we can speak about that. Finally, thermal conductivity. It's interesting to know that we have a strong relationship between thermal conductivity and electrical conductivity. Okay, so try to think to something with very high thermal conductivity that is not a conductor for electricity. This is quite difficult because the mechanism is similar. Okay, so it's very difficult to have something that is going in the opposite direction. Okay, so the thermal conductivity has a good point, at least that is not depending on pressure. So the pressure is not important. Again, not in nanoscale. Nanoscale is another word. Okay, but let's say from 10 nanometers. Above 10 nanometers, about 50 nanometers, we can say that K doesn't depend on pressure, for example. Okay, in solids depends on also on the lattice vibrational waves and the free flow electrons, and this is the reason why it's very difficult to have, let's say, for example, for a solid or a metal and so on, something that is going to be very low conductive for electricity and very high conductive for, let's say, for heat. There is even a relationship for metals that we can use when we would like to estimate how much is the thermal conductivity, and is mainly linked to, let's say, electrical parameters. What is also interesting to say is that we have a very broad range of values for the thermal conductivity. And someone is working with heat pipes. We know that it's possible to have even higher equivalent thermal conductivity using specific system, okay? But equivalent thermal conductivity. This means that is the conductivity that we can derivate using the Fourier law for this specific object like a heat pipe. So then in this case we may have even 100 times the conductivity of copper. Okay, so very ultra high conductivities, but equivalent thermal conductivity. The thermal conductivity is varying with temperature. Here we have, let's say, some example. There are, let's say, systems where the conductivity is really changing a lot with temperature. Other are almost constant. But pay attention that here we have a logarithmic scale. So it seems that it's not changing so much, but it's changing somehow. But for example, from an oxide like aluminum, it's changing, the conductivity is really changing a lot. And another point is that with the metals, for example, when we have alloys, the thermal conductivity of the alloys is always less than the thermal conductivity of the elements composing the alloy. And another point is that we have, of course, a very high conductivity when we are going down with the temperatures. So when we are dealing with the cryogenics, and we are working with liquid helium or liquid gases in general, and we have 100 Kelvin, 50 Kelvin, 20 Kelvin, the thermal conductivity can be completely different. Imagine that, for example, for copper, copper is one of the highest thermal conductivity among metals, maybe the highest, I think. At 300 Kelvin is 400 watt-meter Kelvin, but if you're going down to 20 Kelvin, the thermal conductivity of copper is 20,000. So if you are, let's say, designing a system for cryogenics, all the metals, they are have completely different values of thermal conductivity, for example. And this is a supplementary material. Wow, fantastic. 1002. I was not too bad to start with. This was very fast panoramic view. Something, of course, for you in this audience was something like a resume. Maybe I say something that you didn't know about nanoscales, something that you were not aware. But I believe, I hope, that everything is clear. We are going in progression. So every lesson will be a little bit more difficult, let's say, but it's a kind of, I think there's a warm-up. We can think about a warm-up. So thank you.